Hi, my name is Jim Hogg and I'm a program manager with the compiler team for Visual C++. I'm based here in Redmond on the main Microsoft campus. And over the next 10 or 15 minutes, I'm going to explain auto-vectorization. So first obvious question, what exactly is auto-vectorization? Well, it's a new feature in the C++ native compiler for Visual Studio 11. When I say the native compiler, I mean the one that generates native machine code for x86 or x64 or ARM. It's not included as a feature in that part of the C++ CLI compiler that generates managed code. That's to say, MSIL assemblies. So what does auto-vectorization do? Well, it tries to make the loops in your C++ code run faster. And it does that by making use of vector registers and vector instructions. And I'll explain what these are on the next slide. Well, if it tries to make loops run faster, how well does it do? How much does your application speed up? Well, that varies enormously with the application. However, if you're working upon data elements of ints or floats, that's to say they're each 32 bits wide, then in a tight loop we can reach a speed up of 4x. Another point to make here is that you don't need to request this option with Visual Studio 11. It's on by default. So all you need to do is pick up a version of the Visual Studio compiler. That could be the beta from back in February or subsequent drops that are on their way. Take any C++ code you already have, recompile it, and measure the speed up. So if that's what auto-vectorization does, then how does it work inside? Well, on the right-hand side there, we have a picture that looks inside a chip, either an Intel or an AMD, that's included in all modern PCs. It has various sets of registers. In the middle, there is a set of registers. There's 16 of them in all. It's labeled GPR, which stands for General Purpose Register. 16 of them, and each one is 64 bits wide. However, all modern chips also include another set of registers, and they've done so for about the past 10 years. And these are called vector registers. They're shown on the left. Again, we have 16 of them, but each one now is 128 bits wide. Now you may think that these are useful for holding very wide integers or very wide floating point values. But in fact, the way they're used is to pack several smaller variables into each register. So if we are using ints or floats, again 32-bit values, we can pack 4 of them into each of these vector registers. If we're using doubles, on the other hand, they're 64 bits wide, so we can only squeeze in 2 per XMM register. The registers are called XMM0 through XMM15, whilst the actual instructions that operate upon these vectors are called SSE. SSE itself stands for Streaming SIMD Extensions. And the essence of these vector instructions is that they can perform with ints and floats 4 operations in parallel at the same time. So let's take a look at a simple example of how auto-vectorization works. And on that first line, I have a simple loop written in C++, which simply steps through 2 arrays called A and B. The arrays themselves have a length of 1,000 elements. And for each element in A, it adds in the value of the corresponding element in B. So prior to Visual Studio 11, this is what the compiler would have generated for code to execute that loop. it would have loaded, let's say on the first iteration where I is equal to 0, it would have loaded the value of a of 0 into one of the scalar registers. That's the ones in the middle of the previous diagram. So in this case, we might have had that a of 0 holds the value 1.1. That would be loaded into one scalar register. Then we'd load the value of b0 into another scalar register. Let's assume it had the value 1.2. We'd then add these two together, obtaining the value 2.3 and returning that into the original register. That would be the result that we store back into a of 0. So in order to execute that entire loop of 1,000 instructions, 1,000 iterations, we need to do that same set of operations 1,000 times. What happens with autovectorization is like this. On the first iteration of the loop where I is equal to 0, instead of simply loading in a of 0, we'll load in 4 adjacent values. So in this case, I've shown them as 1.1, 2.1, 3.1, 4.1, and we've loaded them into the vector register called xmm1. Similarly, we load in the first 4 values of the B array into another vector register, let's call it xmm2. Then we issue an instruction which performs 4 additions in parallel. So that gives you the answers 2.3, 4.3, 6.3 and 8.3, which is stored back into the original vector register xmm1, and that is what is used to update the values of A0, A1, A2 and A3. That operation is then performed on all the remaining iterations within that loop. So now we can see that instead of, to complete the whole loop, having to do 1,000 steps through, we can run 4 at a time. So in fact, we only need to do 250 iterations. So this loop would run at most 4 times faster. And down the very bottom of this slide, we see a piece of pseudocode which kind of summarizes what's going on. We've still got the integer variable I, which is running from 0 up to 1,000. But now, instead of incrementing I by 1 each time through the loop, it jumps up by 4. As for the loop body itself, we've tried to denote the effect of what's taking place there as a of I through I plus 3 plus equals b of I through I plus 3, where that range with the colon in between just means the elements beginning at I and finishing at I plus 3. It's not legal C++ code, this is a notation stolen from other languages, but it captures nicely what's going on. So let's look at an example of autovectorization in action. Again, very simple example. We have an integer, a const, which is set to the value 1 million. I've called it dim, meaning the dimension of the arrays that we're about to use, and then declared 2 arrays, A and B, each with 1 million elements. In the main program, we have just one simple loop. We're going to run through every element of A and set it equal, or add into it, the value of sine of B times cos of B. And we do that for each of the million elements in the loop. I should say that I've missed out the code here that puts initial values into the arrays A and B, just to keep the example simpler. So if we compiled this with the VS 2010 compiler, it would generate scalar code, as I've already said. But with the Visual Studio 11 version, it will generate vector code. How much faster will it run? Well, down below, I've got the 2 results measured on the PC in my office. If I disable vectorization, it takes 108 milliseconds. This same loop with autovectorization turned on takes just 37 milliseconds. So that's a speed up of about 2.9 times. That's not as much as the 4x that we would have loved, and that's due to some limitations in this first release of the autovectorizer that we'll aim to remove in subsequent releases. However, at a factor of 2.9 times, that's a welcome improvement over the original performance. Let's summarise auto-vectorisation then. As I've said, prior to Visual Studio 11, the C++ native compiler emitted code that performed only scalar operations. So in a sense, or let me just say, so that means it was either using the general purpose registers for integer calculations or for floating point calculations that actually used the old x87 Wacko stack floating point engine. However, it wholly ignored the vector registers that were already in the chip. However, with Visual Studio 11, the C++ compiler has become smarter. It now tries to use vector registers and instructions to speed up the loops in your C++ code. It emits these instructions to use the vector registers automatically. There's no need for you to change your C++ code in any way. The feature is on by default. You don't need to enable it, request it, set registry entries. It's just there. Even more, it adjusts to the computer that you're running upon. So when the code comes to run, it will sense whether the PC supports a version of the SSE instruction set called SSE2 from some years back, or whether it's a newer machine which supports a more modern version of the SSE instruction set called SSE 4.1 and makes use of the best possible instructions for that loop. A final point is that the transformations that the auto-vectorizer performs in your code are always safe. In other words, if the auto-vectorizer changes your code to use the vector registers and instructions, the answers that transformation gives are guaranteed 100% to be the same as you would have got from the original C++ sequential code. You may ask why I'm making that point. After all, this is a compiler optimization. Doesn't it always do that? The answer is yes. All compiler optimizations are safe. They always give the correct answer. But that's not true of other frameworks that are available for parallelization. For example, if you use OpenMP and direct it to parallelize a loop, it will do exactly what you say. It's your responsibility as the user to make sure that that parallelization was a safe optimization. Finally, for auto-vectorization, to try it out, just get yourself a drop of the Visual Studio 11 compiler, take existing C++ code, recompile it, and run. I'll leave you with 2 links for further information. First of all, a Channel 9 video from a couple of months back, and then a sequence of blog posts. I think we're now at episode 5 or 6, which follow up on that Channel 9 video with further details. Thank you.